The primary purpose of this video is to explain the Milankovitch cycles and how they affect climate change and the global temperature. As a secondary theme, it is also worthwhile to think about what we mean by the term normal. It is often said that the climate is changing from its normal pattern. Is it changing from a normal, stable state of affairs? Or are things more complex than that? We start the video with its central character, the Sun. The Sun is composed of superheated hydrogen and helium gas. Each second, through nuclear fusion, about 600 million tons of hydrogen nuclei is converted into helium nuclei. As a product of this nuclear reaction, the Sun's core attains temperatures of 15 million degrees centigrade, 27 million degrees Fahrenheit. This enormous energy is transmitted to all the planets throughout the solar system. The IPCC used the term total solar irradiance, TSI, to identify the total energy received from the Sun at the top of the Earth's atmosphere. The IPCC states that changes in the solar irradiance are an important driver of climate variability. The causes of such changes are various. This video will focus on those changes caused by the Earth's complex orbital path around the Sun. Milutin Milankovic was a Serbian engineer. During the 1930s, he worked on a theory of climate based on the variations of solar irradiance received by the Earth. He formulated a comprehensive mathematical model describing the varying cycles of the Earth's orbit around the Sun. Milankovitch noticed that these cycles correspond to many indicators of past climate change, such as past ice ages. He therefore proposed that the changes in the intensity of solar irradiation received on the Earth were affected by three fundamental factors. These factors are now collectively known as the Milankovitch cycles. The first Milankovitch cycle is known as eccentricity. A simple model of the Earth's orbit is that we swing around the Sun in a regular manner. But in fact, the orbit varies and fluctuates in complex cycles. In 1609, Johannes Kepler set out three laws. The first law stated that the orbit of the Earth is an ellipse and not a circle, as was believed. We now know that the Earth's orbit is in fact more complex and irregular than a single standard ellipse. The orbit fluctuates from that very close to a circle to that of a more clearly defined ellipse, and then gradually reverts to being close to a circle. The extent to which it varies from a circle is known as its eccentricity. Orbital variations occur over very long time periods of between 95,000 to 125,000 years. The fluctuating cycles tend towards a cycle period of 100,000 years. A major variation in the orbit takes place at around 413,000 years. The net effect being that the Earth's orbit around the Sun is in a perpetual cycle of change. Although this diagram gives a flattened view, currently the Earth's orbit is almost a circle. It is at its closest to the Sun in early January, the point known as the perihelion. It is at its furthest distance in early July. This is the aphelion. When we are closest to the Sun, the separating distance is approximately 91 million miles, 146 million kilometers. And when we are furthest from the Sun, the separating distance is roughly 94.5 million miles, 152 million kilometers. This translates into a current difference in the total solar irradiance of only about 6%. When the orbit is at its most eccentric, the separating distance when we are closest to the Sun is approximately 80 million miles, 129 million kilometers. And when we are furthest from the Sun, the separating distance is roughly 116 million miles, 187 million kilometers. This translates into a difference in the total solar irradiance of between 20 to 25%. The eccentricity of the Earth's orbit evidently causes changes to the total solar irradiance over long periods of time. But its effect becomes more marked when taken in combination with the other two factors making up the Milankovic cycles. The next factor we will look at will also explain to those in the northern hemisphere why their winters occur when the Earth is at its closest to the Sun. Obliquity has to do with how the Earth spins. It does not spin like this in a vertical manner. Instead, it spins with a tilt. The tilt is not constant, it changes over time. Currently, the actual tilt is about 23.5 degrees from the vertical. The full range of obliquity is from 22.1 degrees to 24.5 degrees. To cycle through the full range takes 41,000 years. During that cycle, the tilt does have a significant impact on our climate. In the first instance, it explains how we have seasons and why currently the northern hemisphere experiences summer when it is furthest from the Sun. If the actual tilt did not exist, then each location on the Earth would experience an almost consistent amount of solar irradiance throughout the annual cycle. There would be a slightly increased solar irradiance when the Earth approached the perihelion, but this would not amount to anything like the seasonal change we currently experience. But because of the factor of obliquity, the northern and southern hemispheres experience varying amounts of solar irradiance as the Earth goes through its orbit. In December, the Earth is almost at the perihelion. Due to the axial tilt, northern hemisphere is tilted away from the Sun, and the southern hemisphere is tilted towards the Sun. Thus, the Sun shines directly on the southern hemisphere, but indirectly on the northern hemisphere. Hence, in December, it is summer south of the equator and winter north of the equator. Moving to March, the Sun's rays are more evenly distributed, so it is autumn south of the equator and spring north of the equator. In June, the Earth is almost at the aphelion. Because of the axial tilt, the Sun shines directly on the northern hemisphere and indirectly on the southern hemisphere. This provides summer north of the equator and winter south of the equator. A point to note is the tilt of the northern hemisphere more than compensates for the approximate 6% loss in solar irradiance received at the aphelion. In September, the sun once again shines almost equally on the southern and northern hemispheres. This results in autumn north of the equator and spring south of the equator. There are further variances to the seasons and climate. Not only does the angle of obliquity change over the cycle of 41,000 years, but the Earth's orbit is also going through its cycle of change. This means that the average temperature difference between summer and winter in any particular location will also change over time. There will be two extreme periods. The one extreme is where the axial tilt is furthest from the vertical and the perihelion is at its closest to the sun, thus resulting in a maximum of solar irradiance. The other extreme being where the angle of obliquity is closest to the vertical and the aphelion is at its furthest from the sun, thus resulting in a minimum of solar irradiance. We have completed our look at obliquity and the multiple fluctuations in climate it contributes to. We will now move on to the last of Milankovich's factors, precession. The precession of the Earth is in fact a wobble. It results in the Earth describing a cone over time as it points to different areas of the sky. At around 2017, the axis of the Earth is pointing at Polaris, the North Star. Due to precession, it will gradually arrive at a point where it would be pointing at the star Vega. When this shift does occur, Vega would then be considered the North Star. The full cycle of precession, when once again Polaris is considered the North Star, takes around 26,000 years. Earlier we looked at this example of extreme low solar irradiance, where the aphelion is at its greatest distance and the axial tilt is closest to the vertical. When we factor in precession, there will be further variations in the seasons and a further extreme as the cycles of precession and obliquity coincide. One extreme being where precession tilts the Earth even further from the Sun. Another being where precession tilts the Earth closer to the Sun. Precession also influences our seasons in another way. We are accustomed to the peaks of the seasons, summer and winter, occurring at the extremes of the Earth's orbit, at perihelion and aphelion. This strikes us as logical and the normal state of affairs. But actually, it is just a coincidence. The coincidence comes about because in the northern hemisphere, currently, the perihelion coincides closely with the winter solstice. The determining factors of the seasons are the times of solstice and equinox, where we experience with the solstice the shortest days and longest nights, and with the equinox the two times of the year where day and night are of almost equal duration. Our current situation is like this, but due to the combined effects of precession, obliquity and eccentricity, the equinox and solstice move westward relative to the stars, while the perihelion and aphelion move eastward. This results in the seasons occurring at different points of the orbit. This shift of the seasons goes through a cycle of approximately 21,000 years. For the Northern Hemisphere, this chart represents the year 2017. The perihelion is at the bottom. If we move forward a quarter of the 21,000 year cycle, this would be 5,250 years in the future. Spring would then occur at the perihelion, not the winter as now. In 10,500 years' time, summer would occur at the perihelion, which is the reverse of our present situation. Moving forward 15,750 years in the future, we will attain the same state as that which existed 5,250 years ago. As the seasons go through this cycle, the severity of winters and summers will change, as will the average temperature. The historical variations in temperature have been mapped to the Milankovitch cycles. When sediment cores for the past 2 million years were examined, it was found that the global average temperature cools by 4 to 10 degrees every 40,000 to 100,000 years, and then warms back up again. Now, this seems to strongly correlate with the periodicity of the Milankovitch cycles. But there are discrepancies. For example, there have been glaciations occurring roughly every 100,000 years for the past 1 million years. But before that time, glaciation periods occurred at intervals of about 41,000 years. There is currently no explanation for this change. So I think we can summarize that although Milankovich's theory was more or less ignored until 1976, studies of deep-sea sediment cores have demonstrated a correspondence between periods of climate change and the Milankovitch cycles. In particular, the cycle of ice ages closely matched the theories of Milankovitch. But the cycles do not explain everything, and some inconsistencies remain to be explained. For a full understanding of climate change, there are many more factors to take into consideration. This video has demonstrated the incredible complexity of the Milankovitch cycles and the fluctuations of our climate. Based on this knowledge, it is difficult to decide what sort of climate we should regard as normal, if any. With that thought, we can end with a sequence from the Milankovitch cycles.